Everyone. Today's our lecture in the series in small angle neutron scattering. It's not that you should do the data analysis which is correct, but also what is important is the data you collect and the data you reduce is also correct. So keeping in that in mind, today's the outline of today's lecture is that I would start with the what are the sample requirements and data collection, and then how to get data corrected and normalize. And in data analysis methods, I will not be able to cover everything, but we'll talk about three methods which are very popular in analyzing small angle neutron scattering data, and these will be linear analysis, model independent data analysis, and model dependent data analysis. So when you do the small angle neutron scattering experiments, there are some sample requirements. It's very important to know about them. One thing is that you can measure both solid and liquid samples. And unlike other techniques, even X-ray and microscopy techniques, the requirement of sample in the case of neutron scattering is large. So sample which you need usually are large. And for small angle neutron scattering, you need samples having cross section of around 1 centimeter dia, and thickness you can change from 1 to 10 millimeter. You can see in most of other techniques it's very small. So here it is quite large, and that is because of the flux in the case of neutron sources is not that high, unlike other sources. So if you have a liquid samples, you can fill them in the cuvettes, quartz cuvettes, for which your neutron transmission is very good. So if you have a weak scattering samples, you would prefer to take a thicker samples. So you can go up to 10 millimeter, and the lowest you use is around 1 millimeter. You can go to lower sizes, but what happens? These quartz cells are quite expensive. So one costs around 10 to 15,000 Indian rupees. So if you go to a smaller thickness, then the pouring samples and afterwards cleaning becomes very difficult. So most of the time, the lowest thickness used is around 1 millimeter, and this has width around 1 centimeter, and the length is around 4 to 5 centimeter. And for solid samples, you can use these kind of mountings which are made of cadmium, so that only neutrons they pass through this hole, and over that you can place your palette of solid sample. You need larger thickness for doing small angle neutron scattering, but you should also make sure that you minimize multiple scattering, because most of your formalisms, theoretical formalisms, they are for single scattering. So if you have too much of multiple scattering, then the data analysis become very difficult. So you have to maximize intensity, but at the same time, you have to make sure that you don't have a strong contribution from multiple scattering. Otherwise, data analysis will become very complicated. And as I said in the last lectures, what is important is that you have some idea about how you can do the contrast enhancing and matching in your system, so that you take the proper choice of the medium. So these are very important things before you start doing your experiment or you prepare your experiment. So how do you decide the thickness of the sample for your SANS experiment? Because it is important. So if you take too thick, then your transmission will go down, and if you take too thin, then your scattering will be low. So how do you optimize thickness of your sample? And you do small angle neutron scattering in a transmission geometry. And to understand that what should be thickness, you should know what are the different phenomena happening in your sample. So uh, this is the incident beam with intensity I0. So most of the neutrons, they will pass through. So you will have transmitted beam without any scattering, without any interaction with the atoms, molecule in the sample. And then you will have also coherent scattering, which is taking place from the sample. Then incoherent scattering, and then there will be also absorption of the neutrons. And then, as I said, there is always possibilities that you don't have just single scattering, but the neutrons which are scattered, they can also have a multiple scattering, and that's what you should minimize, because your theoretical models are mostly for single scattered neutrons. And then transmission, is transmitted intensity divided by the incident intensity of the neutrons. And you can write by this kind of exponential expressions, where sigma t is the total macroscopic cross section, and d is the thickness of the sample. So your total macroscopic cross section will have contribution from a coherent part, then incoherent part, and also absorption. And also, you should know that your scattering intensity is proportional to thickness, transmission, and this is a property of the sample. This is differential scattering cross section, which is also property of the sample, means constant. So your scattering intensity is proportional to thickness and the transmission. So transmission, again, you can write in terms of thickness. So this is your scattering intensity proportional to d, and also proportional to this exponential term. So what does this mean? This means that if you want to plot scatter intensity as a function of thickness of the sample, and since you have two competing terms, d and this term, so as a result, this function will have a maximum. So where will this have a maximum? You can maximize this term, and what you get is intensity is maximum at 1 upon sigma t. And if you put this value of d here, so it will be 1 upon u. So your transmission is 37% when your intensity is maximum. So ideally, if from a given sample you want to get a maximum intensity, then your transmission should be around 37%, and your corresponding thickness will be 1 upon sigma t, total cross section. Now you see, in the case when you have, let's say, mostly coherent scattering from the samples, that's what you want. See, other scattering will be giving you background, or you can have some sort of absorption in the system. So if your total cross section is that as given by the coherent cross section, then the thickness which you will select 1 upon sigma t is too large, because see, what you measure is only coherent scattering in the small angle neutron scattering. So in that case, you should be looking for transmission which is 80% or higher than that, to avoid multiple scattering. So if you are sure that there is no absorption, there is no incoherent scattering from the sample, so what is advisable is to avoid multiple scattering, is that your transmission should be greater than 80%. And then if you have, let's say, hydrogenous material, or you have some component which is strongly absorbing neutrons, in that case you can go to the this thickness, actually, where your transmission is 37%, because if you go below this transmission, take thicker sample, then you don't gain, because then your intensity will be low here. And also, if you go for here, and if you go for too thin samples, then again your scattering will be low. So when you have high incoherent scattering from the sample, which in the case you cannot avoid, or high absorption, some elements in the system which absorb neutrons and you cannot avoid, in that case you can go for this kind of transmission to get maximum intensity from the sample. Otherwise, where there is no incoherent and absorption, it is always advisable to go for higher transmission as high as 80%. And 80% transmission, when you take deuterated solvents, in the case of soft matters, you can get this with the cuvettes having thickness 2 millimeter, 0.2 centimeter. And the next important thing is you should know that what is the right contrast for your sample when you want to do small angle neutron scattering. And this is what I had shown also yesterday or in the last lecture. The scattering line density for some of the materials, and this is the calculated scattering line density. And then you could see, let's say, if you have a hydrogenous polymer PEO, then PO will not be good, will not give good contrast when you prepare in H2O. So this is 0.61, this is minus 0.1. But if you prepare it in heavy water, D2O, then it gives very good contrast. Same thing for iron oxide. So iron oxide will have the scattering line density close to that of iron, so around 7. So if you prepare in S2O, then you have a very good contrast, but not in D2O, because then D2O is close to that of iron or iron oxide. And if you have, let's say, some alloys of copper with manganese, so copper is 6.65 and then manganese is this, so it will work very, very nice, but not copper with iron. So if you want to see copper with iron, let's say is this alloy some clustering or something like that, then this will not work in the case of chance. But you have to find the right combination, or at least you should know that this will give you enough scattering or enough contrast in the case of neutron scattering. Then also what you should know is that you minimize incoherent background from the sample. So any heterogeneous content in the sample will give you incoherent background. So you will have the scattering, which is coherent scattering, and plus incoherent background. So if in case you are going for higher concentration of a solute, let's say, but prepared in D2O, where solute is heterogeneous, then your incoherent will increase. And to reduce the incoherent, what you should make sure, as I was saying, that you should decrease that, you can decrease the transmission, but also should make sure that you don't have very high contribution of incoherent background, because if you are have higher contribution of incoherent background, in that case, then what you see here is that your features of the scattering profile at higher Q values will be less pronounced. So you will lose some information which is coming at higher Q values. So if you have higher, let's say, higher content of hydrogen in the sample, then to minimize incoherent background, what is advisable is to take lower thickness of the sample. And this is incoherent background for some of the elements, and you can see that hydrogen has the highest. So once the hydrogen content is in the sample, so if it is above 5-8%, then it is advisable to go for lower thicknesses, 1 and 2 millimeter. But if it is less, close to 1-8%, then even you can take thicknesses up to 5 millimeter. So this was about how do you prepare correct samples for your sans measurement. So one thing is that you should take the right thickness, because that will maximize the intensity from your samples. So if you have more samples, then in given beam time, you can measure larger number of samples. So that is important. Otherwise, what will happen is you may have higher incoherent background, and or you are able to measure only less samples with proper statistics. And also you should know that select the proper constituents so that you have a good contrast in the samples. Now, once you have prepared the right samples and also done the measurements, what is important is you correct the data properly, because as you measure your scattering intensity in the transmission geometry, so there will always be transmitted beam contribution in the scattering you measure, and obviously there will be always background in the sample. So you should correct your scattering from the sample for first is for your transmission and second is for the background. So basically, whenever you have scattering from the samples, you will also make two additional measurements. So one will be from the medium or the solvent itself, and the third will be the background. So, and then how do you correct is this is the expression you one can derive this expression also. Uh, so this corrected intensity from the sample for solvent and background. So it is solvent, and then you have background term and divided by the transmission of the solvent. So you should also know the transmission of the sample and also the solvent. So this is scattering intensity from the solvent minus background divided by the transmission of the solvent, and this is the transmission of the sample. So this is the expression by which you can calculate the corrected intensity from the sample. Then another important thing is that scattering intensity, what you correct, should be normalized to the property of the sample. So what is the property of the sample? Property of the sample is this term, which is differential scattering cross section per unit volume. This is the property of a sample, so that whenever and wherever you measure, it should be the same. It is like the density of a material. So density of a material at a given temperature or conditions should be same, and if it is not matching, then it will depend on the technique you are using. So similarly, here for a given sample, it should match wherever and wherever you measure. If it is not matching, then it could be related with the resolution of the instrument. So because different instruments will be using different geometries, and that could lead to different resolution, and that could be leading to some differences in the differential scattering cross section you will be measuring. So from this, then you put this value of I corrected, which comes from this equation, and then this is the final expression for the corrected and normalized scattering intensity. Okay, so ठीक है, I will. So what I was telling was that when you have the sample, then you should make two more measurements. So one will be solvent and another will be background. So your corrected intensity will be I, this is from sample, minus I, this is background. You can have, okay. And then transmission of the sample. So this is one term. And then you will have another term which will get subtracted from this term. That will be the solvent you measure minus again background divided by the transmission of the solvent. So this will correct for this will be IC. Then what is also important is Mhm. Yes. Okay, so what is also important is whatever corrected intensity you get, you have to normalize it to property of the sample. And how do you do? Then you have this corrected intensity is equal to, then you have some constant, then thickness, then transmission, and then this is okay. So this last term is the property of the sample, which is differential scattering cross section per unit volume. So now you know everything actually. So you know what is your uh, scattering intensity, corrected scattering intensity, then thickness, transmission, and this is what you would like to have, normalized scattering intensity. And this is instrument constant, and this is determined from the standard sample, because in the case of a standard sample, you will be already knowing this. So by measuring this, you get this one. So how to do that? Here you can see. And then, as I said, it's the property of the sample, so it should not matter. But since you have different instruments with different resolutions, so if there are differences, it could be related with the resolution function of the instruments if you are doing the correct measurement. And how these two are related. So this is the actual or the theory part, uh, and it will get converted with the resolution function, and this is what you measure. So you can see this is going to remain same irrespective of which instrument and where you are measuring, but this will change. So this depends on, and this depends on three factors actually. So one is what is the collimation of your beam. Second is what is wavelength resolution you are using, and the last one is what is the detector resolution you are using. And in the case of small angle neutron scattering, you can write your this Q resolution by these two terms. So one is which is coming from wavelength part, and another is coming from the divergence of the beam. So delta theta by theta and delta lambda by lambda. And this with delta Q, in the case of collimation effect, is a constant as a function of Q. But in the case of wavelength, it will increase as the value of Q increases. But in the case of small angle neutron scattering and the length scale of interest, to get enough scattering in the feasible time, uh, usually you have this delta theta by theta of the order of 10 to 15%. So once your delta theta by theta is of this order, then there is no point you can tie to your wavelength resolution. So diffraction experiments, you have this of the order of 1 to 2%. But in the case of small angle neutron scattering, you don't gain by tightening this. So also delta lambda by lambda which are used are also order of 10 to 15%. So you can see your resolution, Q resolution in the case of SANS is not very good, and it is unlike that of typical diffraction. So I think in one of the first talk, one of the slides I had talked about velocity selector is used to change the wavelength and also wavelength resolution. And how do you select a particular wavelength and the wavelength is spread? So this velocity selector consists of helical slots, and these slots are made on neutron absorbing drum. So anything which is not passing through these helical slots will be absorbed. And since it's not a straight slot, so when you rotate this drum with the high speed, so your frequency is around 10,000 rpm. So the neutrons which are going very fast or very slow will not be able to pass through this helical slot, because this helical slot will synchronize with the particular speed of the neutrons, and they will only able to pass. So if the speed is slow, so your slow neutrons, that is high wavelength neutrons, will pass, and if it is moving with very fast speed, then the fast neutrons will pass. And then there are different ways you can make these helical slots, and one of the ways is called multi-disc. You create multi-disc at having synchronized with the passage of neutrons at different places, forming a helical slots. And then in each disk you will have this kind of distribution. The passes through which the neutrons can pass through, so transmission region, and also we'll have a region where your neutrons are absorbed, and they are synchronized to give you a helical slots. Alpha is the pitch. So this is the angle moved by the velocity selector on one rotation. So as the neutron will pass from here, this end to this end, how much angle this drum has moved, that is called the pitch. So typically, I think few degrees, usually this has H is Planck constant. And then L is the length. So length is typically about a feet, 30 or 40 centimeter around. And omega is the frequency by which it is rotated. As I said, typically around 10,000 RPM. So that decides your lambda. So you can move from, let's say, 4 angstroms to 20 angstrom. That is typically used in case of a small angle neutron scattering. And then this is the transmission. So depends on what is the angle subtended by your transmitting region. So if you don't know the resolution function of your instrument, so you may be making error in calculation of polydispersed. And this is because in both the cases, your data are smeared, and if you don't know the resolution function, then you can expect this smearing coming from the polydispersed. And therefore, to get the correct value of polydispersed, it is important to know the resolution function of the instrument. So now coming to data analysis methods. Before that, I would say that there are two kinds of scattering patterns you can see when you do the small angle neutron scattering. One is dilute system, where your scattering is monitoring, and this width of the distribution is equal to the size, and also you will have different functionality deciding the different morphology of the structures in the system. And in this case, your intensity is proportional to the form factor. And when you have concentrated system, then you see a peak in the scattering pattern, which is coming from your SFQ, structure factor. And this peak typically comes around 2 pi by d, where d is the distance between the particles. So in the case of small angle neutron scattering, what you are seeing is interparticle structure factor, not the intraparticle structure factor. So it is interparticle structure factor. And if you want to look at intraparticle structure factor, how, let's say, within a particle, how your atoms are correlating, then you have to go to higher Q values. And for that, you have to use high Q technique. And in small angle neutron scattering, since you are looking at a length scale of the order of the particle, so only you see the interparticle structure factor. And how will you know that your system is dilute where there is no contribution from structure factor? And this comes from the scaling of the data on dilution. So if you have a given concentration and you measure some pattern, then you dilute this system, let's say by a factor of 2, and then you can scale the data. It means there is no structure factor. And if you are not able to scale the data by the dilution factor, then it means that there is a structure factor. So that is a proof of knowing that there is a structure factor. So coming to different methods of analyzing data. So the simplest one is linear analysis. So what this method tells is that irrespective of any shape of the particles, if you curve where the slope will be given by 2. And by knowing the slope, you can get the value of radius of gyration. So that is simplest thing you can do. Just plot your data in the low Q region, log intensity as a function of Q square. And if you see a linear curve, and then from that slope, you will get the radius of gyration. And if you have some idea that your particles are a sphere, then you can get radius from this expression. And if you know they are rod, and if you know one of the dimension, you can get other dimension. This is commonly used because it doesn't need any detail analysis. So if you want to know the detail analysis, then there are two methods used in the literature. So first one is model independent chance analysis. So what you do in this method is you measure this term P of R, which is peer distance distribution function, which represents the distribution of distances between pairs of points within the particle. So basically, what you have to do is do the inverse Fourier transform of scattering intensity, and you will get P of R. And what information this P of R gives is the following. So what is shown is your scattering pattern for different shapes of the particles. And as I told that your profiles will be different for different shapes of the particle. But if you do the inverse Fourier transform of these patterns, you get P of R. This should be P of R. So it is just in one. It is asymmetric distribution. And the extent of P of R gives you the maximum dimension of the size. So in the case of a sphere, the the R maximum will be the diameter of the particle. In this case, it will be the length of the particle. In this case, it will be overall size of the food cell. And in this case, it will be overall size from this end to this end of this thing. So, by doing the Fourier transform of scattering intensity, you can get the P of R, and P of R uh, gives you the because it is different for different shapes of the particle, so it can give you the information about the shape of the particle in the system and also the maximum dimension of that shape which is there in the system. So R is calculated by the indirect Fourier transform. You just don't do the indirect Fourier transformation because of incomplete data due to limited Q range. So if you want to do inverse Fourier transform, then you need data from Q range 0 to infinity, which experimentally you don't get. And if you don't get that, then you need to extrapolate your data to low Q value and high Q value. So that will give you the systematic errors in the calculation of your P of R. So what is used is called indirect Fourier transform. This was a method proposed by Glatter very early, around 1977. And what is assumed is, that the shape of your particle will have a maximum dimension. And within that range, then what you do is you express P of R as a linear combination of orthogonal basis functions. So these basis functions would be like spline functions, and you can take these orders from, let's say, 1 to say 15, 20 kind of functions, basis functions, and then these coefficients are determined by the least square method. So you place this value here, and then you already know your intensity, and then you do the least square methods. So it's not directly, but you are doing in steps. That's why it's called indirect method. And then from there you can get the P of R. And once you get P of R, then you get the radius of gyration from this expression, and also overall size of the complex from the Dmax, as I already said. So this is how indirect Fourier transform is done to calculate P of R, and which can give you the shape and the effective size like Rg of the particles. But you don't get the detailed information about the structure in the system. So this slide shows P of R for spherical particles. So as I said that in this case, this will be symmetric, and also the maximum extent here is the diameter of the particle. So this is 2.5 nanometers, so it goes up to 5 nanometer. And then when you have different sizes of the particle, so your radius is changed from 2.5 to 10 nanometers. So the width is decreased for higher size, and then the corresponding P of R looks like this. So you can see the larger size, 10 nanometer, the extent of P of R goes up to 20 nanometer, and these are different for different sites. So you can differentiate by measuring P of R, different sizes of the particle. And in the case of rod-like particles, so this is asymmetric. Your P of R is asymmetric, and again the maximum dimension is the length. So your D max is related to the length of the cylinder. And then when you have radius fixed and different lengths of rod-like particles, then in the scattering pattern you get these linear regions determined by the reciprocal of the radius and the length. And then again you can differentiate them, different sizes of the rod-like particles as your P. So this shows P of R calculation for malaria disease, for mosquito diseases like malaria, dengue, then you have to understand this receptor handling different diseases. So what we have done was prepare this sample in D2O to get good contrast. So this is your scattering pattern. And then to know that what is the structure of this protein, because one good thing about a small angle neutron scattering is that you measure samples in the native condition, that is And this is the P of R calculated for this scattering pattern. So you can see there is additional hump in the P of R at higher. And what does this mean actually? So if you have one spherical monomer, then it is symmetric. If you have this elongated structure, if you have dimers in the system, so this cannot be explained by the monomer, because so it could be either this two monomers attached sidewise or headwise or this way or that way. So different possibilities are there, and the detailed modeling is difficult to get from the uh, calculation of P of R. And also, if your system is concentrated and you want to look at the interaction, it is also difficult. So to get those kind of information, you have to go to the model calculation. What do you do in this case of model dependent chance analysis? You select a model for possible structure and interaction, then fit the experimental data using selected model, fix the value of known physical parameter as many as possible. So because you are fitting the parameters, so it is always good to freeze the parameters which are known. So lesser the fitting parameters, reliable will be the fitting. And once with these model structure and interaction, you see, is it a good fit? So if no, you go back, change the model, and then again come here to see whether it is a good fit. And when you see that is it a good fit, means your reduced chi-square will be close to 1, then you can say, okay, it is a possible model. So it cannot be the final model, but it could be only a possible model, because you which can minimize your reduced chi-square, but not necessarily the right model for your system. So to decide a final model, what you should do is you should take help from the complementary techniques. So otherwise, your model may not be right. So you should make use of complementary techniques to verify that your possible model would be the final model, because it's a model fitting. So you cannot be sure about what is the exact model in the system. So how do you model for form factor? So you have form factor. You have different functionality of form factor. So many times looking at your scattering pattern, you can come to know that what could be the possible structure in the system. So then you can think of rod like kind of a structure in the system. If you see a slope of 2 in the intermediate Q range, then you can think of this like. So like that, some observation from scattering intensity can be used to start the model for form factor. And this will be a starting model. And similarly for interaction, you can start by looking at the features in your major scattering intensity, particularly as I had explained in the first lecture, that if you have a strong repulsive interaction in the system, then for repulsive interaction, your S of Q in the low Q region will be low. And when it is attractive, it's divergent, it's quite high. So to assume whether your interaction is repulsive or attractive, you can look at low Q regions. So that would help you to start the model to fit structure factor. So once by looking the features in the scattering intensity, you have some initial model to start form factor, and also initial model to start structure factor. Then you can fit the data. So this is one of the data where what you are looking is you have protein in the solution, and you are adding some salt where you know that salt can modify the interaction between these charged protein. And then interestingly in this proteins sample, what you see is when you go to very high concentration, look at phase transition. So protein goes from a dilute phase to a rich phase in protein at higher salt concentration. And then, as I was saying, that you can look at the measured data, the features there. So, for example, in this case, you can see uh, when at low salt concentration, you have a correlation peak. And then as you increase, you have a buildup of scattering intensity in the low Q region. And once you have a buildup, then you can have, first thing is your repulsive interaction is modifying, because at low Q value it is low. And then it could be your interaction modifying. So how do you fit? Now you have two interactions. One is repulsive part and one is attractive part. So you can assume a potential like this, which has attractive part and repulsive part. And for both of these potentials, you have two parameter. One Z2 for repulsive part, and this is the magnitude of your attractive part, and this is the magnitude of your repulsive part. And then this z, since it's going within the exponential, so it's basically represent the range of this. So reciprocal of this will be the range of the potential. So if z is a small value, then it means your potential has a wide range, and vice versa. And then you see you have fitted for this system proteins at different salt concentrations, K1Z1 and K2Z2. And you could see K1 is decreasing, K1 is increasing, magnitude of your attractive part is increasing. The data goes up and up when you add more and more salt. And then range Z1 is decreasing, means range is increasing. And on the other hand, K2 is decreasing and Z2 is increasing. And since these are repulsive part, and you can correlate this with the existing theory, like for repulsive part of charged particles, you can also assume this as given by the DLVO theory, Debye-Huckel kind of potential. And then from that, so what happens in this case, you can see the fitted data. So they fit well to the experimental data. That your repulsive part is suppressed as you increase the salt concentration. And this is the total potential, your attractive plus repulsive. So at very salt concentration, is enough. So let's say at average distance of the particle, when it is greater than already is known in the literature. So you can model for both attractive and repulsive. Then coming back to this CQM protein, so from PFR you get the information that this protein exists as dimers, one of these possibilities. But once you do the model analysis, where you can model for individual unimer, what is the size of this unimer in the dimer. So that we model with the form factor of ellipsoidal. and where the semi-major axis is found to be 13.8 angstrom and semi-major 19.9. They are like ellipsoidal shape, and also you can model how these are connected with each other. So what we found was the distance between two unit is about 45.5 angstrom. Model analysis, you find that this is the possible structure of divergent systems. So there you can see that your D will be of the order of 55.5, and they are not spherical, non-spherical universe. So this can come from by combining your P of R calculation with the model analysis. Then this is a very important thing with small angle neutron scattering, because you measure scattering intensity in the normalized scale. So this scatter intensity is measured in the unit of differential. So you know this part. So if you know the other terms, you can calculate the contrast in the system. So for example, since you measure scattering intensity in the normalized scale, you already know this left hand side term. So that means if you know the other terms, you can calculate the scattering land density of the protein. So, for example, in these calculations, we know most of the terms. We know the volume fraction. We know the V because we have already modeled this term. We know P of Q, we know S of Q. And then we calculate this contrast, rho P actually. So, the proteins mostly, they will also be hydrated by the water. So, it is different from the non-hydrated protein, which comes around 3.8 into the 10 centimeter minus. Is attached to the protein, and that comes out to be 20% water attached to the protein. So this term and any unknown thing on the right hand side of these expressions can be obtained. And this shows the modeling of different size nanoparticles. So you have the curve measure from different size nanoparticles, and one thing is you see in overall scattering, uh, let's say from this TM40 is larger than other two nanoparticle systems, and plus what you see other case you don't see. So it means where you see the form factor oscillations, your polydispersity will be low compared to others. You fit this with the form factor of a spherical particle, and then since you don't have many oscillation scenes, it means systems are polydispersed, and for that you come log normal distribution, and normal distribution is account of the larger size of the particle. So if you fit symmetric distribution like normal distribution, then it is not possible because very large sizes. But if you add large sizes, kind of distribution which can have a long tail, then it is the correct distribution to fit the large sizes of the nanoparticles. Along with this, others have higher qualities per se, and you don't see the oscillations. Okay. And this is much larger than other two, so scattering intensity is larger and the width is also smaller. So uh, this slide shows analysis of data from a charged micellar system. So In this case, what is important is not to know what is the structure of these micelles, but also what is the interaction between these micelles in terms of how much condensation of these counterions are there, because this condensation is very will modify the interactions between these head groups, which are also charged. And once details of this I will cover in the next lectures. But what I am trying to show here is that since these are charge systems, so again you can fit a charge axis will be the same, and also one is spherical shape, one axis must charges around. And what you see is in the measured data is your correlation peak shifting towards high Q values. But it is not a straight line. So it means there are some structural transition taking place. So in the case of structures, but since there is a change in the slope of the peak position where it occurs, clearly shows that somewhere there may be a structural transition of and then you can see how these and then how small tails pack to the structure from the size of these micelles. That increases as you increase the concentration, and also you measure basically the charge on the micelles, and from that this charge you can calculate the count and condition, which will be 1 minus z. And then always you can use your analysis to the particles. And if they are not contrast matched, then you have 4 terms. As nanoparticles, then you only are left with 2 terms. So this simplifies your analysis, because then in this case you have to model for 4 terms. But in this case, you need to model only for 2 terms, and your analysis becomes easier. Your fitting parameters will be less in this case. And this is what the data has been fitted in detail. So in this case, you have nanoparticles and you increase the surfactant concentrations. So you can clearly see there is buildup of scattering intensity in the low Q region as well as higher Q regions. So this happens because your this number of micelles adsorbs, they increase as the surfactant concentration increases, and this is adsorption isotherms you calculate from the detailed modeling. So how number of micelles adsorb on the nanoparticle, and if you already know the form factor, you can calculate the structure factor. So this is the calculated structure factor for these systems. So you can see as number of micelles increasing, the build up in the low Q region increasing, and your peak positions remain same. Only the prominence of these peak contribution at the peak position enhanced basically. So what happens? Unlike concentration effect in solutions, where your distance is important, in this case, within the particle, when these nanoparticles are getting adsorbed at the surfaces, then this structure factor is decided by the excluded volume effect. So if already you have one uh, the particle, other micelles cannot come. So what matters is now the diameter of the micelle and the diameter of the nanoparticle. This is for when you compare two different size of the nanoparticles. So your these are the diameter the nanoparticles, different diameters. So what we have done is same weight percent we have taken, uh, concentration of the nanoparticles. Surface area is different, to volume ratio is different. So what we found out is maximum adsorbed micelles. So when the nanoparticle is small, it only adsorbs 15 number of micelles on the nanoparticle. But as increase, then it increases from 15 to 65. And then this is adsorption coefficients from the adsorption isotherm. And then packing fraction is very high for the larger size particles because of curvature effect. But fraction of adsorbed micelle is decreased when you have the size is increased. And this is because of surface to volume ratio. So to conclude, what I would like to say is when you want to do the all these things are important to prepare to measure the samples correctly, also to do the data reduction correctly, and also we want to collect good quality science data requires to consider the correctness for sample and contrast conditions. So you should be knowing what is the correct thickness and also what are the right contrast conditions. So without that, it will be very difficult to get the correct data. And once you have got the correct data, then you should make sure that you are correcting for the transmitted beam and background contributions. So if you don't do this, then again your analysis will not be correct. And then you should also normalize your corrected data to the proper units. And as far as analysis is concerned, you can do both model independent, model dependent analysis. And please note that there are a number of free data analysis software available online. But the important ones which are often used are these ones actually. One is SAS data analysis, another is SAS. And download them and use it. And also, once you have done the analysis, so that's not the end of your thing. What you should also compare is that how the complementary techniques support the model used. So you should also have the data from the other complementary techniques to support your model, and that will make your analysis final. Then you can have more confidence on your data analysis. Thank you. So you can let me know if there are questions. So questions, you can ask questions. If there was any doubt, please let me. Okay, so thank you.